Hello. We're going to now look at the core technique for building point distribution models. I'm going to use PCA in order to encode the statistical variation in whole families of objects. Let's start with a little bit of abstraction right here. So let's suppose we've got a whole set of objects from that same class. They're going to have some sort of embedded variation in it. And let's assume that we can describe something about the boundaries of the object. Here we're just going to work with two-dimensional objects. So we're going to have a set of point positions that talk about the boundary of the object. If we were looking at our flat shapes that we were looking at previously, these could be the corner positions. The example we're going to work up with is these T-shapes, so this will be at each of the corners, the vertices of the T. So let's assume that we've got that data. And we're going to assume that there is some kind of a structural variation about these T-shapes. So it's not going to be like a T-shape has all these points moving in a completely random sort of way. We're going to assume that largely there is some sort of systematic variation between all of these shapes. Unfortunately, because we're capturing real image data and the lighting changes and the cameras have funny little effects, the measurement of these point positions is going to vary a little bit. Excuse me. And for that reason, we're going to want to use a Gaussian distribution to model the variation of this noise or these small variations. So we're going to assume that these point values are correlated. And what we would like to do is to try and build some sort of model which captures this correlation. That's to be the structural model, and then also obtain some sort of a statistical model afterwards. The reason why we want the statistical model is we want to be able to capture the range of variations that are normal to this family of shapes. So the structural model says how can they vary, and the statistical model says how much can they vary. And once we have that model, then we can use that model that we built for recognition. So there's going to be a training stage here where we build the models of the objects we want to look at, and then there'll be a recognition stage where we actually use those models themselves. So here's an example of shapes. Okay, it's a hand, okay, obviously, and we're just going to assume the hand is flat against like a tabletop or a background or something like that. And we can go build a silhouette around that object. And we're going to start with this example because it's one of the famous examples that was used when the people first invented and developed the ideas behind these point distribution models. And then after we've looked at this example a little bit, then we're going to be able to move on to our own shapes. That's the T-shapes that we're looking at. So you can see there's quite a lot of variations in the position of the fingers and the orientation of the hand, and also one could maybe look at different sizes and shapes of hands as well too. But mostly here we're just going to look at the variations in the finger positions, and you can see an example set right here. Well, we're going to assume that we can get a set of points that go around the boundary of the object. So we can do that. They could be either like the tips of the fingers and the notches between the fingers, or it could be actually all the individual points that go along the boundaries. In any case, it's a set of points which describes that actual shape. And then we're going to use a kind of trick. So given that set of observations, and these are our boundary points, there's P of them, and here's our row and column coordinates. So this is a set of two-dimensional points. We're going to do a slight trick, and that is we're going to take all of these points which are originally two-dimensional point positions for all the P points around the boundary of the object, and we're going to make one new long vector by concatenating the row and column positions of all of these individual points. So we originally had P points, each of which was two-dimensional, and now we're going to create one new point in a higher dimensional space that has 2 times P values in it. So it's going to be a 2 times P dimensional space right here. So we started with n original boundary descriptions, and now we've got 1 point, 1 vector for each of our examples of a much higher dimension. And that's going to be where we're going to start with. Now we want to look at is how can we encode this new set of data in a much more compact form which makes explicit the structural variations. And that's where using the point principal component analysis is going to come in here. If we assume that there was some sort of systematic variation, then if we plotted these points in the high dimensional space, which is hard for people to understand, but you can sort of conceptually imagine, at least in 2 dimensions, if there was some sort of systematic correlation, then these points would be drawn out over, for example, a line in 2 dimensions. And what we would like to do is find that line, find that systematic relationship. If there was no variation, then all these components will be uncorrelated and it'll be just a great big ball of points with no structure to it. And that's where the PCA comes in, is we can look at those points in this high dimensional space and then we can use PCA to find the correlations. We can find the axes of sort of related variations. So how are we going to do that? Okay, well, we're going to use this sort of standard PCA type method. Okay, we've got our vectors right here. Here's the original 2p dimensional vector, and we're going to express it in terms of a mean vector and its principal component axes. And that will give a complete and accurate description of the object. But in fact, actually, we're going to want to only use a subset of those values. Instead of using all 2p of the different principal components, we're only going to use a smaller subset m. And this is for 2 reasons. One is it allows us to reduce the data so we don't have to work with so much numerical data. It improves our accuracy. Second, if we choose our m well, we will be looking only at the structural variations that are embedded in the data and not all of the noise. And we'd like to make sure that we've got the structural variations are represented in the m and all the rest that we can sort of throw away. We'll see how to do that in a minute. Okay, so we've got our data, and we're going to re-represent it in terms of these weights, okay, using the standard sort of principal component analysis type representation. And that will give us our new description for each of these objects. It will be a much lower dimension, hopefully, so n will be a lot smaller than p, and it'll encode our structural variations. It will be possible for us to take this and reconstruct approximately the shapes that we had to begin with by this formula right here. That will give us approximately this x again. There will be a little bit of variation because we didn't include all of the terms, but we haven't really lost too much provided we choose our m well. So here's an example of what you might get with the hands. Okay, so here we're going to look at the first 3 modes of the eigenvector if we had a data set of all these different hand positions. And you can see along here this is the first mode, the second mode, and the third mode. And they varied it from one extreme of the mode to the other extreme of the mode. So you can see here the fingers go from very far apart to very close together. As the first mode, the second one is really more related to the thumb. Notice that the thumb is quite here, close into the hand, and the other one is quite far from the hand. And the third one is the sort of this middle finger is kind of moving back and forth between the index finger and the fourth finger right here. And there may be other modes of variation to this hand data, but these are the first 3 that were selected, the very common ones. And it's also a kind of standard way of representing this sort of variation, is that they take the mean value and they sort of take extremes of the mode in one direction or in the other direction to kind of make explicit what the variation is right here. It's a kind of a way of visualizing to help people understand what the variation is. Okay, well, once we've represented the shape in terms of these W vectors, we're now in the position of being able to build a statistical model of this. And we're going to use a multidimensional Gaussian model to represent the family of expected shapes that we will obtain from the training data. We'll assume that it's a kind of normal or Gaussian type distribution. And just in this case, because we're working now with a reduced dimensionality of m, we'll have a Gaussian distribution that's in a higher dimensional space. That's m. But building that model is quite easy. We take our original set of x vectors, we project them down into our principal component space, and now we've got our w vectors, and we've still got n of them because we have our n training samples. We can estimate the mean of that new statistical distribution. That's the t right here, and we put all of those together. We can also now estimate our covariance matrix that we need for our Gaussian distribution, and that's given by our scatter matrix right here and scaled. So we've got an estimate of the two parameters that we need for our multivariate Gaussian distribution, the mean vector and the covariance matrix. So that's going to encode the shapes that we expect to see. So that gives us a kind of the building pieces, building blocks that we need in order to put together our principal component analysis and our point distribution model of our T-shapes that we're really trying to recognize. We've got a point distribution model that encodes the structural variations, and then we also have our Gaussian statistical model which encodes the natural variations that we find in the models. And now we'll see how we can put that together to recognizing and representing our T-shapes. Thank you.